is a new edition number 4 of the Dasp workshop, Autonomic Solution for Autonomic Parallel Data Stream Processing. It's a pleasure to start this workshop. I would like to share my screen just to see with you the program of the workshop. I hope that you can see my screen. Today, first of all, communication. The proceeding of the workshop are available online on the ACM website, so you can download the extended abstract of the 2 keynotes that we have today, together with the proceeding of the other regular paper accepted at this workshop, and also for the other workshops of the conference. Today, the organization of the workshop will be the following. Just 1 second, the program. Okay. We start with the first keynote from Vincenzo Colisano. The title of this keynote is Motivation and Challenges for Stream Processing in Edge Computing. Then we have a first paper presentation, Elastic Pulsar Functions for Distributed Stream Processing. Then we have a short break. And then after the break, we will start again with a second paper on an online approach to determine correlation between data streams. And finally, we conclude with another keynote by Marcos Assunção. The title is Towards Elastic and Sustainable Data Stream Processing on Edge Infrastructure. The workshop is organized by me, Gabriele Mencardi, from the University of Pisa, together with my colleagues Massimo Torquati from the same University of Pisa in Italy, and Valeria Cardellini from the University of Rome, Tor Vergata, in Italy too. So I think, Valeria, we can start with the, I don't know if I'm forgetting something, but I think that we can start with the first keynote speaker.
Yes, we can start. Thanks, Gabriele.
I will interrupt the sharing of my screen. It's no longer needed. So I have the pleasure to introduce the talk of Vincenzo Colisano. Okay, this talk, the title, I repeat, is Motivation and Challenges for Stream Processing in Edge Computing. Vincenzo Colisano is an associate professor at the Department of Computer Science and Engineering at the Chalmers University of Technology in Gothenburg, Sweden. Vincenzo Colisano holds a PhD in computer science from the Polytechnic University of Madrid in Spain. And his research focuses mainly on stream processing and its use in cyber-physical systems such as smart grids and vehicular networks, covering aspects such as distributed, parallel, and elastic processing capabilities, streaming-aware data structures, edge computing, taking into account security and privacy aspects, scheduling of use of resources, stream processing provenance, and finally, porting of machine learning analysis from the edge to stream processing domain. So, Vincenzo, are you able to share the screen? Yeah, thank you, Vincenzo.
Can you hear me?
You here. So I will leave you the floor.
Okay, so you can hear me and you can see my screen, I guess.
Yes.
Yes.
Thanks.
Okay, so thank you for inviting me. I am very happy to give this talk about motivations and challenges for stream processing in edge computing. So I will start. So first of all, I work at Chalmers. It's an university in the south of Sweden. The city is called Gothenburg. And the group I belong to, it's called the Distributed Computing and Systems Research Group, the DCS group. And we are part of the Computer Science and Engineering department at Chalmers. So we are 25 members on average in the group, including faculty and students. And we focus on these 3 areas mainly, so distributed systems, cybersecurity with privacy too, and stream processing. And the last one is actually the topic we are going to focus on during the talk. When it comes to the talk, I will briefly introduce what edge computing is and also what stream processing is for the ones of you that are maybe not super familiar with these topics. And then I will discuss 3 challenges that I think are interesting for future research based on my experience and the experience based on the work we have done in the group in the last years, and then conclude. So before I start, let me say that, if we take as a starting date for the research in stream processing, that is debatable, but let's take one, let's say 20 years ago, when the first papers about stream processing and the first frameworks were made available, we're talking approximately 10.5 million minutes, and there are hundreds, if not even thousands, of researchers working on this, and now you get me to talk for 30 minutes, so I guess it's clear I will just mention a tiny fraction of what has happened during these 20 years, but ask me if you want to talk more about specific things. I am connected in Slack, and you also have my mail address in the first slide. I can share the slides afterwards, so we can talk more if it's needed. So let's start with edge computing. We have heard many times that edge computing is about pushing the analysis towards the edge and try to go beyond a bit the traditional approaches in data analysis that are basically, first you gather the data centrally, you collect the data over a certain period of time, then you do some offline analysis, and then you have your insights about what is happening in the system. So the reality is that we have in our modern cyber physical systems and digital systems, we have a lot of devices, and their cumulative power is considerable. Here we have 2 examples, smart grids and the big networks. The idea is that if we successfully manage to push the analysis towards the peripheral devices, then we can enable a lot of interesting, useful applications. I'm not going to list all of them, but I can mention here congestion monitoring. Let me take the congestion monitoring. So, if you look at the traffic in your cities, you can predict where you will have a congestion, or at least detect it. And then once you detect it, you can give routing suggestions to vehicles that are nearby, and so on and so forth. Now, if there is a lot of research going on in edge computing, it's because, of course, there are challenges that we still need to address. And these challenges in edge computing connected to cyber-physical systems, they stem from the unique characteristics of these systems. Again, you have a list here. I will not go through all the points individually, but if I just take support for mobility, for example, you probably agree that when you connect to a car, well, the car might be off, first of all, so you cannot really connect to it. It might enter a tunnel, so you can lose connectivity. You can directly talk with a car, or you can talk with cars through roadside units, so computers basically deployed along the roads. In such a case, there will not be a static connection between one car and one roadside unit, because cars are moving around. It might be that actually a single vehicle is in reach from multiple roadside units, and then you have to take this into account so you don't analyze the data twice, and so on and so forth. So based on my experience and also what is discussed in the literature, the summary when thinking about edge computing and research in edge computing is that we need to take into account the following things. The infrastructures we have, they are not designed to collect and gather all the data that is sensed. It's physically impossible. A modern Volvo car, and I use Volvo because we are in Sweden, it's between 20 and 30 gigabytes of data per hour. no way you collect all this data from hundreds of thousands of cars over years. Where do you store it? Why would you store it? What will you do with it? We have latency constraints. It actually takes time to get large amounts of data, analyze them, and send them back. So you really need to rather push the analysis towards the devices rather than the data towards the central servers. And of course, there is always the concern of security and privacy. When you can collect a lot of data and it's fine-grained measurements, it's very easy to know who you are, where you go, who you meet, and so on and so forth. So it's also for that reason that if you manage to push the analysis towards the devices, maybe it's not a formal guarantee or proof of privacy or security, but you make the life of the attacker a bit harder. So it's still a good idea. So now stream processing. Why stream processing then in edge computing? Again, if we go back 20 years more or less, the idea when they introduced stream processing was to shift from the traditional database approach in data analysis, which is first the data, then the query, writing applications that are about how you store the data and then later how you query it, to first the query, then the data approach. So to define so-called continuous queries, continuous applications that are always running in memory, that are not created only when you want to read something from a table. You send continuously data to them and you continuously produce results. In fact, in stream processing, an application is defined as a graph of operators and streams. You have operators that are generating data. These data items are called tuples. You have operators that are receiving the outcome of the analysis to give it to other applications or to the user. And in between, you have operators that have both input and output streams. They take tuples, they transform the tuples, they analyze the tuples, and they produce new tuples. As you have standard operators in a database, you also have standard operators in stream processing and in stream processing engines, which are the frameworks where you run streaming applications. So you have two types, stateless operators. As the name suggests, they don't maintain a state, they process each tuple individually. You can use them to filter data or to transform data, to change basically the attributes of a tuple. And then you have stateful operators. They are the same you have in a database. So you can aggregate tuples, multiple tuples, and you can also join tuples. In this case, the join is not between two tables, but rather between two streams. Now, if you use modern stream processing engines, you can use these operators. You can define your own operators if you want. The nice thing is that you can compose these operators into applications that are semantically rich. This is an example, a simple one. You can, of course, do more complicated analysis than this. But you want, for instance, to raise an alert if a car is speeding, if it's going faster than its average speed. Can you do this with a streaming application? Yes, you can. This is a way to do it, to compose basic operators. You could start by actually discarding data you don't need. Then you could aggregate the data to compute the average speed. And then you could join this aggregated data with the raw incoming data. So basically, whenever you get the latest position report with a speed of a certain car, you could enrich this tuple with this join, adding the corresponding average speed in the last 30 days. Now that you have a tuple with both speeds, you can send them to a filter, and the filter can decide whether it should forward the tuple because it's an alert, it's a situation you want to detect or not. So why I'm mentioning all these things, streaming, in the context of edge computing? Well, because it turns out that streaming is quite expressive. You can make semantically rich applications easily composing these operators. Well, easily, it's arguable, depending how skilled you are, but at least you can. You get online analysis. So these applications, as I mentioned, they don't store the data. They continuously process the data as the data is being sensed. But one of the important things here is that you also get almost for free parallel and distributed analysis. If you write your application as a graph of base operators and then you give this application to a stream processing engine, then the stream processing engine can help you deploy the analysis both in a distributed and in a parallel fashion. What does it mean? That we have, if we have our vehicular network and we have this application we want to run, well, of course, we can run it at a central server, we gather the data and we do the analysis. But on the other end, we can also deploy these operators at each roadside unit. If the roadside units, the cars and the central servers, if they are connected, from the perspective of the stream processing engine, it doesn't really matter. You can deploy the operators wherever you want. In this case, of course, you need to take into account, as I said before, that a roadside unit might be getting data for a car only during a period of time, and then the car might connect to another roadside unit, but without going into too much details right now, you can still deploy the operators. You can do even better. You can place one operator inside the car, for instance, the map, so you remove all the sensitive information that does not leave the car, and you only forward to the roadside unit the data that you actually need to process. So hopefully you agree with me that this is a good starting point for edge computing, because at least we have an infrastructure that allows us to push the analysis, to move the analysis towards the peripheral devices. So what are the challenges then? I'm going to describe three of them. As I mentioned, these are based on the research I have conducted together with my group in the last years. So the first challenge is about actually pushing the analysis to the edge. What does exactly mean to push the analysis to the edge? An intuitive or direct way of understanding what it means to push the analysis in stream processing is, of course, to take some operators, it's what I just showed you, and study how to actually move them, run them in the peripheral devices. This has been done for 10, 15 years at least, under different names, operator scheduling or operator placement. And I'm citing two references here. You can find a lot of them in the literature. This is something you can do, and it's worth investigating. It's, of course, it's a good practice. But what I think it's interesting is that this is not the only thing you can do to leverage edge devices. I think we can be more creative, and we can still find new ways of leveraging the power of the distributed devices, not by just giving part of what we are doing already in a server. There are different ways to go here. You can actually keep the semantics of the applications, of a certain application you are running as they are, but actually add more operators, extra work, and still benefit from the edge devices. And I will show you an example of this in the next slides. You might also try to decompose your analysis into smaller units and then study how you can move them, or you can even distribute your analysis so that you take advantage of physical properties of the system you are trying to analyze. And I'm putting here a reference for the ones of you that are interested in this particular aspect. But let me focus on deploying new operators. So this is an example of a collaboration with Volvo from 2 years ago. So here we want to perform clustering of Lidar data. The Lidar is a sensor, is a 3D scanner that has, it's a column of rotating lasers that are sensing the environment and creating data sets of three-dimensional coordinates of basically all the objects they have around. Now, if you cluster this data, you find objects, so points that are close by, and these points can represent objects in the physical space, so a car, a tree, or a building, and so on. Here, what we wanted was to gather many point clouds from multiple lidars and then cluster them to create, for instance, a 3D map of a city. So the problem was that we could not run the clustering within the car. One, because it's expensive. Second, because each car has its own data set, but we want to aggregate multiple data sets, and cars are not really allowed to exchange this data between them. On the other hand, we could run it at the server when it comes to the computational power, but we had the problem of transferring the data. One of these sensors generates several megabytes of data per second, and if you want to get the data from many sensors, the infrastructure is going to become a bottleneck. So what we did was to, as I'm saying here, deploy new operators. So we kept the clustering running at the analysis center, at the central place where the analyst sits. So we didn't touch really that part of the application. Instead, what we did was to study whether we could create streaming operators able to compress and decompress the data. It's a streaming operator, so it was not just about applying, zip compression over a file and sending it, so that thanks to the compression, we could decrease the volume of data and actually manage to cluster it centrally. So this compression we used, it's a lossy compression, so we could introduce errors during the compression, but with a limited bound. It's done using piecewise linear approximation for the ones that are interested, but not really important at this point. And here I want to show you a result. I'm going to go through the different parts here because it's a bit complex. But what we found out, for instance, is that if we allow a maximum error when we compress this data from the Lidar sensor of 1 meter, so basically when we allow a maximum of 1 meter in the error of position of a specific point sensed by the Lidar, in practice, we never reach such a limit. The median value is around 20 centimeters in error, but the compression in the data we achieve is significant. We can reduce the original volume by 95% by introducing an error, which median is 20 centimeters. And if you want to detect a car that is in front of you, plus minus 20 centimeters are sort of okay. It's not an application that is used to stop your car if there is a problem. It's just to get an idea of what you have in your surrounding environment. The good part is that not only you get 95% compression of the data, but the quality of the clustering compared to the one you can achieve when you have all the original data, it's still good. The accuracy here is 90%. Okay, so this is just an example showing that you can leverage the power of edge devices, but we never move the clustering from the central place. We are actually doing more stuff now, but still we can now manage to transfer the data and cluster it centrally because we can reduce the volume by using the computational power of the computers we have within each car. That's the second challenge I want to mention is that of awareness, hardware, data, and system awareness. So I just took one slide from a keynote given by Professor Gibbons some years ago about how you achieve performance in big data applications, and this is connected to awareness. So what he said is that you should first scale down your application, so make sure that you do just the analysis you need to do to get your result, maybe through approximation, as I just showed in the previous example. Then make sure you scale up your application so you really use the computational power that you have within each node. And if that is not enough, then scale out, go for a distributed execution. So I think there is a lot of research in stream processing that can be done to understand the differences between scaling up and scaling out and actually create systems that are first scaling up and then scaling out. So let me explain what I mean. To explain this, I need to introduce briefly how we boost the performance of streaming applications in 99% of our stream processing engines nowadays. So you create your application and you have your operators. And as I said before, you can run these operators in multiple nodes. You can run them distributedly. When you want to increase the performance of the query, what you usually do is that you run operators in parallel. You create multiple copies of the individual operators. You give portions of the state to them, and then you send to them data according to the portion of state they maintain. To make a very simple example, which of course is not something you will do in practice, if you have an operator analyzing data from the cars to compute the speed, as we were seeing before, you could have these multiple instances and say one only processes data from red cars, one processes only data from green cars, and one processes data from other colors, okay? Now, I don't have time to go too much into details, but there is something that is important here to know. We do this in existing system using shared noting parallelism. What does it mean? It means that we assign each portion to an instance of a parallel operator of the overall state in an exclusive manner. Each instance has its own portion of the state, and it's that instance only that is going to access that portion. It's shared noting. The instances are not really sharing the state between them. Each one has its own portion. And to make sure that this has this exclusive access, we also need to use dedicated communication channels, queues, basically between the instances of the different operators we have in an application. Now, when you want to ensure that your parallel application is going to run and produce results correctly, despite the fact that it's running in parallel with shared noting parallelism, again, I cannot go too much into details, believe me, you need to pay attention in the order in which you process data within each instance, or at least the conditions under which you trigger the production of results. You cannot just process data in any order it arrives, because otherwise that might compromise results. Why do we use shared noting parallelism? Well, among other reasons, we use shared noting parallelism because it allows both to scale up and scale out with the same mechanism. You don't particularly need to care whether you are scaling up or out with shared noting parallelism. You have your operators, you assign them to threads, you assign threads to processes, and then you assign processes to nodes. If two threads are running in the same process within the same node, or two different processes at two different nodes, from the correctness and synchronization perspective, it doesn't matter, because each one has its own state, its exclusive access, and they have dedicated communication channels, so it doesn't really matter. The problem is that this is not acknowledging that the left side of this figure is not equal to the right side of this figure when we want to maximize scale up before maximizing scale out. And the reason is that the right portion of this figure has shared memory, while the left side, it does not. If you properly leverage shared memory, you can significantly increase the performance of application. Here, I just want to show some results from previous papers. So here we have another query. It has 4 operators, and then we have the parallel version of this query. We have 2 instances of each operator, and we are adding these extra operators, they're called mergers. They are sorting the data, and this is to enforce correct execution. Since each operator needs its own portion of the state, and we need dedicated queues, under the hood, if you look inside the actual thing that is deployed by the framework, it turns out that it looks like this. You have the operator instances, these are assigned threads, then you have all these dedicated queue for them to communicate, and these extra operators, the mergers, are there to enforce correctness. The thing is that if you know that all these operators are running in the same node, sorry, and they can share memory, then there are better ways to synchronize them. You don't need all these individual queues and extra operators. You can use dedicated data structures. ScaleGate is one such data structure that we developed in the group that leverages shared memory to synchronize in a cheaper way the different operators when they exchange data and still support correct execution. And this is what happens to the performance of the application. Here you have shared memory parallelism, and here you have shared noting parallelism for increasing parallelism degrees of one operator in this query. And here you have the throughput, the number of tuples per second that the operator can sustain. This is actually thousands of tuples per second, okay? So you see that when you increase the parallelism with shared memory, the throughput keeps growing. You can reach up to 500,000 tuples per second being processed by the query. On the other hand, if you have shared noting, sure, it keeps growing because you are putting more resources, but it doesn't scale as good because part of the extra resources you put are there to synchronize and make sure that the application is producing results correctly. So it's not that all the extra computing power you put, it's actually spent analyzing data. It's actually spent synchronizing threads. And that overhead you can totally avoid if you take advantage of shared memory. Which brings me to the third challenge, which is that of model-driven adaptiveness. So adaptiveness is one of these topics that has also been extensively discussed in the literature in stream processing. Adaptiveness means that basically you are able, or your system is able to dynamically adapt to changes in the environment where you are running a certain application, so that, if you have, for instance, more data to process, you can provision more resources to process this data and so on. So you can dynamically adapt the system to react to changes in its environment. There are a lot of ways in which you can make a system adaptive. These are some discussed in the literature for stream processing. You have load shedding. You might decide to discard some data if you cannot process all the data. You have balancing, of course, you have provisioning and decommissioning, so elasticity in stream processing. You have scheduling. You can take actual scheduling decision from the operating system perspective. You can take decisions about how you place, where you place operators, and so on. So now there is something happening that we all are aware of. So there is a lot of research going on right now in machine learning and artificial intelligence, and it's appealing because in principle we can get help in taking decisions about how to adapt our systems by having, self-learning tools rather than human experts that are there to take decisions. But this doesn't really make it less challenging. There is an obvious challenge that we are all aware of, that is the fact that adaptiveness is something that needs to happen continuously. It's not something, you take one decision and then you are done. You have to always monitor what is happening and then react to it and go back to monitor again, and it's a continuous process. The other problem that is a bit more subtle is that there is no a clear partitioning of what each technique can do and can be used for. They overlap. The border between them is sort of blurred a bit. So if you want to reduce CPU consumption, you could shed load. Just discard some data and you have less data to process, and that will reduce your CPU consumption. But you also might change the scheduling priority of the threads running your application. The application will run less, data will accumulate, and maybe who is sending you the data through back pressure or some other mechanism will stop sending so much data, and you will still use, or this will still result in less CPU consumption. Then, of course, there is rebalancing the load, either using the resources you have or even provisioning new resources and putting them in different nodes and so on and so forth. So in this context, I think something that is still worth investigating more is the use of models, precise models that can explain what is going to happen. And I think this is something we should do to condensate and distill the knowledge we have from many years of research and pour that into self-learning tools rather than ending up reinventing the wheel, because it happens periodically, and it's not only in stream processing research, of course. So I just want to show you two small examples. These two graphs are from two different experiments that we conducted to assess how good our model of the behavior of a stream join was in predicting throughput, so number of comparisons per second run by a stream join, and latency. If you look at the graph in the upper part, it's a bit complicated, so I will just tell you what the main message here is. There are two lines, a blue one, which is basically the comparisons per second the join is actually doing in the real system, and the green line, which is what our model predicts the join is doing. And the reason you cannot see the blue line is because it's exactly the same as the green line, and it's behind the green line. So the main message here is that if you have a precise model, you actually can predict extremely well what the system is going to do, depending on, for instance, the load or the amount of tuples it has to process. You can do more. Here we are looking at latency. So here we have a system that most of the time it's not saturated, and this you can see when this latency here is flat, meaning it doesn't have a lot of work to do, we can do it, and the latency is very, very low. These are seconds, so we are in the sub-millisecond realm for the latency. But then you see that all of a sudden, you have these huge spikes. This is logarithmic, so here you see we go from sub-millisecond to actually seconds of latency. Of course, to get a super accurate prediction when you have these jumps in 3-4 order of magnitudes, it's more complicated, but still you can have a good prediction. What is the point here? If you are able to have such prediction and they are accurate, then you can support systems that are taking adaptive decisions, for example, an elastic system, because you can easily distinguish cases in which you clearly need to provision more resources because the system is going to be overloaded over a long period of time. You cannot afford that. For other situations in which, well, there will be a small amount of time during which the system will be overloaded, but it's not that bad. It will be absorbed rapidly in a couple of seconds. And this kind of knowledge, I think, can be extremely beneficial when you have systems that maybe are threshold based and would immediately react as soon as they see that the latency is growing beyond a certain threshold. Okay. And that's basically it. So to conclude, I wanted to share some insights and knowledge based on the research we have done in the group. And I thought these three challenges are interesting, or at least I believe there is actually research that still needs to be done along these three lines, which basically are about what exactly it means to push the analysis to the edge. I would probably say that we need to find better ways to leverage the computational power of edge devices rather than really pushing the analysis. Sometimes there is nothing that you really need to push. You can keep your stuff where it is. You just need to add more stuff. About awareness, I really think we still want to have modular systems, simple systems, but we don't really take advantage of the real power we can have within each node. And I'm not entering into discussions here about actually having hybrid analysis using, CPU and GPUs at the same time, and maybe even FPGAs at the same time, and moving the load and the computation between them in real time. And then something that is about, I think it's extremely important to keep decreasing at least the chances of reinventing the wheel and condensating what we know while making a transition through systems that have more and more self-learning components that are taking decisions for us, so that we don't, well, maybe waste is an exaggerated word, but let's say so that we use all the stuff we have investigated in the last years. And that would be all from my side. I don't have more slides, and I think, yeah, it's 35 minutes, so I should probably stop now. Yes.
Thank you, Vincenzo,
Thanks.
for your presentation. Thank you for this very interesting presentation about the future directions of stream processing on edge computing. I would like to ask the people, the attendees, if there are questions. This is the right time to ask questions. No question. I checked it in Slack. There are no messages.
I have one question, if I can.
Sure.
I'm Massimo Torquati from Pisa. First, thank you very much for this very interesting presentation. I want to just understand your position concerning the awareness point, the point that here in the slide that you are presenting is point 2. In particular, I would like to hear a little bit more about your vision for tackling this problem. I mean, do you think that having a sort of a unified model for both scale up and scale out is the direction, or instead, do you think that it's better to having specialized models for different systems and try to integrate them in some way that I don't know basically, but I would like to know, understand what do you envision in this direction?
Yeah, I think that if what we are after is really to squeeze the computational power we have in the devices, then we will be able to squeeze more if we have dedicated solution to scale up and dedicated solution to scale out. They can be complementary, they can coexist, so they don't need to be different systems. Actually, I think that would be an interesting challenge. But I mean, this is at least what I've seen in many of the papers I was working in with my group in the last years, that you can scale better when you are really tailoring when you're really aware of the hardware you are using. If that is what will happen eventually, that I don't know. I mean, you end up having ugly code. It's not as elegant as something that can both scale up and out at the same time. Personally, I believe we will still end up with different systems. So systems that are lightweight, they are only working within individual nodes, but they are really able to scale up for within each node, and other more general systems that are about distributed execution, but they will be suboptimal in scaling up. Yeah, if you look at the evolution of stream processing engines, for instance, I think there were components in the pioneer ones like Aurora or Borealis that were significantly more advanced than the ones you have now in Flink, for instance. They have been removed because, of course, it's hard to maintain code when it looks like that. But now we are researching how to do the same things they were doing back there, but from outside SP rather than from inside. So I don't know to which extent it really pays to not having tailored solution. Let's put it like this.
Thank you. Thank you.
Thanks.
I have also a question, but it's more technical, maybe. If I remember, is slide number 26, probably. I'm not sure, but I hope. Okay. Yeah. I don't really get the distinction between, in terms of model, between the shared memory and shared nothing, in the sense that, okay, shared nothing is the classical one in which if you have an operator with a state, you partition the state in the different instances of the operator, and you guarantee that each of these instances will receive data that touch that specific partition of the state. No? But yes. What instead, in terms of model, what do you mean with shared memory? In the sense that you have a state that is shared, and so you need to introduce synchronization, but you need to guarantee the ordering of the inputs.
So I can make a specific example. So I'm looking at the videos I see here in my Zoom here. Okay, so let's say that me, Valeria, and Massimo, we are exchanging data with you. So we are 3 parallel instances of an operator, and you are the operator that comes next. You are not parallel, you just take the data from the 3 of us. In shared nothing, we need to work independently of whether we are in the same node or in 4 different nodes. So I will have a queue that I use to share data with you, Valeria will have a queue, and Massimo will have its own queue. Now, if you are request to sort your data before you process it, because the analysis you're running is order sensitive, then in this case, for me to give you a tuple, it's O1 cost. I put it in the queue and I'm done. For you to process a tuple, the cost will become linear in the number of queues, because you will need to wait for at least 1 tuple from each queue, and you will need to check each tuple you have in a queue and pick the one that is the next you should process. If they have a timestamp, the one with the lowest timestamp. Okay, but if we are in shared memory, then we can all share one data structure rather than individual queues. So what happens now? That since we share the same data structure, we can also share costs. For instance, we could have a priority list between us. So when I give you a tuple, it's my responsibility to insert it in order in this shared data structure. And when Valeria gives you a tuple, she will do the same, and Massimo will also do the same. Okay. So for us now, the cost will go from O1 to O log n, because we need to do a sorted insertion in this data structure. On the other end, for you now, the cost will no longer be linear in the number of queues because you have a single object. You just need to take the next tuple when it's time to take it. Okay, I'm simplifying a bit the data structure, but for the sake of the discussion, you can take now a tuple in O1. So by leveraging the fact that we share memory, we can redistribute the cost of sorting, having log n for us, O1 for you, rather than O1 for us, log n for you, n for you. And we can even parallelize it better. And this is basically what is happening in these experiments. Since the sorting cost now is parallelized and it's also decreased to log n rather than n, it scales better. So these are the tricks you can play basically when you acknowledge the fact that you are sharing memory.
Okay, I understand. Now I understand that probably the advantage is, in this case, is related to the sorting part, not to how the state is maintained, rebalanced in case of...
In this particular experiment, yes, this is about sorting, at least the results I'm showing here. There are benefits in state maintenance too. I'm not presenting them here, but something very simple you can imagine is that if we are aware that we share memory and we want to redistribute the load, we don't need really to transfer state. Yes. I don't need to serialize my state and give you my state because you can directly pick it from the shared memory. This is actually something we have in a paper we presented 2 years ago, I don't remember. There are a lot of benefits in shared memory, and I think there are still many that we don't know,
okay,
or that we don't leverage.
Thank you so much, Vincenzo. I don't know if there are other questions. They are welcome. We have a couple of minutes probably at most, or we have to start. Other questions?
As I said, I'm also... Oh, sorry.
Thanks, Vincenzo, for the very interesting talk. And I have just a question about one of the topics you mentioned about pushing the analysis to the edge. So if I understood correctly, your suggestion is to redesign the application to run in the edge, so to exploit better edge devices rather than offloading some part of the computation just to the edge.
Yes.
So are you thinking about automatic tools that can be able to redesign in some way the application, or is it a task of the developer?
That's a complicated question. I think there is a lot of room for improvement in letting automated tools translate what we want to do into how we should do it in streaming. I did some work on it, especially when it comes not just to analysis over time, but spatial temporal analysis, and maybe leveraging, spatial temporal logics and other formalisms that exist for the analysis. I'm not aware of such thing really happening, but I think it's definitely interesting. I mean, it's a known fact that you can implement the semantics of an application in many different ways, and sometimes it's up to your creativity to find the next one. So probably an automated way of doing that, it's definitely something that would be interesting. I cannot give you a better answer than that, unfortunately, because I don't have it.
Okay, I think that. Thank you, Vincenzo, again.
Thanks. And
I think
if you
there
want
are
to write me in Slack, I can answer in the next days, and you have my mail address. So of course I'm available.
Thank you again. So I think there are no other questions. So I would like to thank you again, Vincenzo, for to do this talk to us today. It was a pleasure. So now we can go on with our program for the Autodesk workshop. Thank you, Vincenzo, again.
Thank you.
I will leave the floor to Massimo, who will present the next paper. No, Massimo.
Yeah, I was wondering if we have a break here or a small break, and then we restart in a while, or instead we go directly straight away. So I don't know. Do you have a, because in my original program I think that papers should start after 5, right? Or am I right?
5, yes, 5:10. So we are a little bit early, but
I don't know. But I think we can wait a while, have a rest, let's say, and then start respecting the program, right? No?
Okay. For me, it's okay. We can wait, I think, 15 minutes, 10 minutes, and then we can start. Okay?
Yeah, okay. That's it.
Good. Of course, in the meanwhile, if somebody have questions about the talk or any other thing, we are here and we can answer. Vincenzo probably is here. So connect and talk.
Yes, I'm here, still here.
Thank you, Vincenzo.
Good. I think we can start. We are more or less on time, and we are stick to the scheduling of the talks. So we now start. Welcome back. Welcome everybody. We now start the paper session for the Autodesk workshop. We have 2 papers in this session. The first one is elastic pool. As you can see in the slide, elastic pools are functions for distributed stream processing by Gabriele Russo, Antonio Schiazza, and Valeria Cardellini from University Tor Vergata in Rome. The presenter will be Gabriele Russo. So you can start, I think. Thank you, and everything fine. Go.
So hello everyone. I'm going to present this work, which is on elastic pulsar functions for distributed stream processing. So just to recall some concepts that have been well discussed in the keynote, we know that we can regard data stream processing as a reference paradigm for real-time data analytics. We know that DSP applications are usually represented as directed acyclic graphs in which we have operators and data streams. So the operators are the processing elements which apply some transformation to the input data, and they exchange data streams. And the goal of this kind of application is to process high volume data flows with very low latency. To do so, the class of the DSP system we are particularly interested in this work is distributed data stream processing, in which we scale out the execution of the operators to leverage multiple cores, but also multiple computing nodes. And as we heard in the keynote, there's an increasing number of DSP applications which run not only in the cloud, but also in fog and edge computing, where they can be closer to the data sources and the consumers. So in practice, we usually run multiple parallel replicas of each operator. So basically multiple threads or multiple processes to cope with larger data volumes, so that each replica can process a share of the input stream. The problem is that analytics workloads are usually characterized by variability, which means that it is difficult to statically determine a good parallelism level for each operator. And so a key feature for stream processing systems is elasticity, which is the ability of dynamically changing the parallelism of operators at runtime, so to be both efficient and cost effective, so to avoid both over provisioning and under provisioning of resources. Indeed, elasticity has been an active research topic in the field of data stream processing for more than a decade. And in the literature, we can find really a variety of solutions which differ from each other with respect from several dimensions, such as the metrics which are used to make elasticity decisions, with, for example, throughput, latency, utilization. We have different control architectures because most of the existing solutions exploit centralized controllers, but we also have a few works that explore decentralized or hybrid control schemes. We have a variety of methodologies to derive autoscaling policies. So, for example, threshold-based policies, control theoretic methods, reinforcement learning, and so on. And also we have, for example, reactive approaches or proactive approaches. So really we have a lot of different solutions in the literature. A key issue for the adoption and the application of elasticity in the context of data stream processing is the overhead that often characterizes parallelism rescaling, which makes it difficult to have seamless rescaling at runtime. In the literature, we have a few works that have addressed this issue for single node multi-threaded DSP engines, where you can be quite efficient in rescaling. But if we consider distributed DSP systems, and especially the most popular ones, such as Storm or Flink, they lack support for seamless operator scaling. And so every time you change the parallelism of an operator, you may experience basically a spike in the latency, because you have to preserve the integrity of the internal state and the integrity of the stream itself. So you need to pause the processing for even a few seconds, which may be it may have a significant impact on the performance. So the goal of this work is to integrate support for seamless elasticity for DSP applications running on top of Apache Pulsar, which is a messaging framework which can run, as I will explain in the following, streaming applications. So this work revolves around the integration of low overhead operator autoscaling in Pulsar, the implementation of a few elasticity policies, and in particular threshold-based heuristic and queuing theory-based policies, and then the evaluation of our solution on a realistic application. So Apache Pulsar is a cloud-native messaging platform. It is open source, and it features a lightweight computing framework, which is called Pulsar Functions, which allow users to perform some computation on the received messages. Pulsar has a 3-layered architecture. We have a serving layer made of brokers. Then we have a storage layer composed of bookies, which are instances of Apache Bookkeeper and which take care of persistent message storing. And then we have function workers, which allow users to execute a user-defined logic. And Pulsar is highly scalable because each of the 3 layers is designed with scalability in mind, and it is able to ingest millions of messages with very low latency. So this makes it appealing for stream ingestion. But we are mainly interested in Pulsar function for this work because this component enables stream processing on top of Pulsar. Pulsar functions are inspired by the function as a service paradigm. The idea is that users define functions and they associate each function with a topic. So what happens is that every time a message is published to the topic, the function is executed taking the new message as input. So it can apply the user-defined logic to each message, and possibly the function will publish a new message to a different topic. So it is easy to realize that if we define several functions and interconnect each function to the other ones, we can set up a complex processing pipeline which processes a stream of messages. So functions are executed as threads or processes within the function workers. Functions are stateless by nature, but we can still run stateful operators by storing the state externally, leveraging Bookkeeper, which is the same data store that is used to persistently store the incoming messages. Pulsar allows users to configure the parallelism level of each function, so you can have multiple parallel instances of the functions. The problem is that every time you modify the parallelism of the function, all the instances are destroyed and then the correct number of instances is recreated from scratch by Pulsar, and this of course introduces an overhead, which is not what we want. So to accomplish our goal, we extend the functional workers and introduce new components which implement the well-known MAPE functionalities, that is monitor, analyze, plan, and execute. So our new components take care of all these steps required for implementing an elastic streaming solution. The monitoring component observes the arrivals of data to the topic, so it records information such as the average arrival rate and so on, and it also monitors the function execution so that we can have information about the average function execution time. Based on this information, the analyze component characterizes the system state at any time, and the planning component can run a policy that we define to make scaling decisions based on the current state. And finally, we have to execute these actions, so we need to update the parallelism, hopefully with low overhead. So to remove the overhead that Pulsar introduces every time we perform rescaling, we improve the mechanism that is used for parallelism update. So in particular, we want to avoid terminating and restarting the function instances. So what we did is that simply we refactored the update command that is provided by Pulsar to update at runtime the functions, and so we only launch or terminate the instances as required by the planned actions. So we modified the logic so that you don't need to terminate all the instances every time. In this way, when you, for example, add a new function instance, the other instances are never paused, so they continue processing the input data, and there's no performance degradation in the process. So we also have implemented a couple of policies to evaluate our solution. So we started with a simple yet popular threshold-based autoscaling policy, and what we did is that we defined the policy looking at the backlog size, that is basically the queue length in the topic, so the amount of messages that are ready for processing waiting in the topic. So this is the reference metric we used for this policy. The policy requires two thresholds, T-in and T-out. When the backlog size exceeds T-out, we add one instance. When the backlog size is below T-in, we remove one instance, provided that we have at least two instances in that moment. So this policy is very simple. Also, it's simple to implement, but of course, as all the threshold-based approaches, it is really not aware of the desired service level we want to achieve. So it requires manually tuning the thresholds to achieve a different behavior. So we also considered queuing theory-based autoscaling policies, where the idea is that we can model DSP applications as open queuing networks, in which we model each function as a station, and in particular as a GG key station, because in Pulsar, all the function instances can be regarded as multiple servers, which all process data coming from a single waiting lane that is the topic. So to evaluate the the waiting time of this queue, we resorted to the Allen-Cannin approximation, which gives us the average waiting time. To do so, we needed to collect some information online by means of the monitoring component. In particular, the formula requires us to monitor the coefficient of variation of the arrival times to the topics, the coefficient of variation of the departure time, so basically the completion time of the functions, and the utilization of the function instances. So based on this model, we defined a policy which considers two different scenarios. In the simplest one, we consider a maximum response time requirement for each function, and we use a greedy approach. So we use the formula and we pick the minimum key, so the minimum parallelism level, such that the requirement is satisfied. But this scenario is not really realistic, because usually you have a response time requirement defined looking at the whole application. In particular, we assume in the second scenario that we have response time requirement on the end-to-end paths in the application graph. So basically every path usually corresponds to a query, and you define a maximum response time, so maximum processing latency you want to achieve for that query. So what we do is that in this case, the total response time is evaluated as the sum of the function response time along the path. And we again use a greedy approach. In this case, we start with the minimum parallelism level for each function at every iteration. And then what we do is that we scale out the bottleneck function, so the function with the highest response time, until the requirement is satisfied. So we performed some experiments deploying Pulsar on top of Kubernetes in the cloud. For the experiments, we used an image recognition application, which is composed of 3 functions. We assume that users publish a stream of images to a Pulsar topic. These images are sent to 2 functions in parallel. The first function resizes the images and stores a copy of the image. The other function also resizes the images, creating an even smaller copy, which is then fed to a third function, which uses a pre-trained TensorFlow model to perform object recognition. So, for example, to detect malicious content, something like that. So for the experiment, we used a synthetic workload in which we generate images with exponential inter-arrival times, and every 10 minutes we change the average arrival rate. And we compare different policies. So we consider the threshold-based policy we defined, the queuing-based policies we defined, and also consider in the comparison a work published in the literature, which is called DS2, in which the idea is that you try to estimate the true processing rate of each operator, taking into account effects such as the blocking effects due to congested upstream operators. And once you have estimated the true processing rate of each operator, you determine the parallelism level you need to sustain the input rate. So this is a throughput-oriented policy. So we first consider the threshold-based policy, in which we set the scale-out threshold to 150 tuples, that is messages, and the scaling threshold to 50 tuples. What we can see looking at the right-hand side of the slide is that the policy manages to keep the backlog size between the 2 thresholds for most of the time. So it works, but it is completely unaware of the latency we achieve. So for example, in this experiment, we achieved an average response time of 23 seconds, which is likely not idle. But of course, we can achieve a different behavior by changing the thresholds. But the point is that you cannot really be sure that you achieve the performance you want without resorting to a trial and error approach. Instead, for the queuing-based policies, we can explicitly set some response time requirements. In particular, we set a very strict requirement in this case, which is 1 second, which is strict because the TensorFlow based function is quite computationally heavy. And the policy manages to keep the response time almost within the threshold. So the average response time is 1.303 seconds. It is quite conservative because it determines the optimal parallelism level as 5, and it keeps it for the whole experiment. Then we consider the other policy, which is the S2, and it lies in the middle between the threshold-based policy and the queuing-based one, because it achieves a good response time, which is 2.7 seconds, and it performs frequent reconfigurations. And the interesting thing to observe is that in spite of so many reconfigurations, there is no evident impact on the processing latency. You can see some gaps in the response time plots, but those are caused by the monitoring of the response time, not induced by the reconfiguration themselves. So in conclusion, we have integrated support for elastic stream processing in Pulsar, and we have implemented different auto-scaling policies, which allowed us to rescale the functions with negligible overhead. So for future work, we aim to implement proactive elasticity policy through workload forecasting techniques, and also explore the opportunity of having multi-level elasticity, so scaling the function workers in the cluster along with the function instances. Thank you for your attention.
Thank you very much for the presentation. Very nice presentation. Are there any questions from the audience?
Yeah, I would like to ask just a curiosity, because I don't know Pulsar in particular. I'm not familiar with this framework. First of all, the presentation and the work looks very nice, because you compare also different policies, for making the streaming application adaptive. Okay, this research problem is still hot, but not new, in the sense that many people in the past tried to study similar problems for other systems, also for streaming systems. So I'm wondering if there are, I don't know if there are, but it's a question for you, if there are specific challenges for applying elasticity in Pulsar compared with what in the past other people did in systems like Storm, for instance, or Flink. Do you think there are specific challenges related to the architecture of Pulsar that could make this research problem more challenging, or not?
Mm-hmm. Actually, the reason we wanted to explore Pulsar is that its architecture looked appealing for having low overhead scaling. So the idea of having all stateless function instances looks attractive, because you may, in theory, you can rescale them with no overhead. So that was the idea, which is which is different of what you have, for example, in a more traditional streaming platform, which is optimized for streaming, but it often requires complex protocols to ensure state integrity in case of rescaling. Actually, when we performed some preliminary experiments, we discovered that it was not really so easy to achieve seamless elasticity, because the architecture supports it, but the implementation did not support seamless rescaling. So we needed to do some work, but eventually the message is that having a function-oriented architecture enables seamless rescaling differently than what happens in Flink, for example, or Apache Storm, Spark Streaming.
Thank you so much for your comprehensive answer. Thank you.
Nice. If there are another question, we have 1 minute or less, basically, because now there is the break, coffee break. Unfortunately, no coffee, but anyway. Any other question? Okay, so let's thank again Gabriele for the very nice
Thank you.
presentation. In any case, if you have any questions, you can send, you saw the email address of the authors of Gabriele in the last slide. So in case, please do not hesitate to send questions or comments or whatever to the authors so they would be, I think, more than happy to answer.
Yes, of course, I'm also on Slack.
Good, very nice. So now we have a break, and then we start to 10 to 6, yes, 10 to 6. So, and then we will have our second paper. Okay, thank you again.
So it's visible now?
Yeah.
Okay.
Seems everything works. So I think we can start. You can start your presentation. Next paper is, as you can see, an online approach to determine correlation between data streams. Devesh Kumar Lal is in charge of the presentation. It's a joint work with Dr. I'm sorry from the pronunciation. Probably it's better that you pronounce your name.
Yeah.
Okay. So
okay.
Go on, please. Thank you.
Hello, everyone. I am Devesh Kumar Lal, pursuing PhD from School of Computer Science and IT, Devi Ahilya University in India, and under the guidance of Dr. Ugrasen Suman. And today I'm here to deliver a presentation on an online approach to determine correlation between data streams. So these are the table of contents. First, I will go through the backgrounds of data processing, and then I will explain the different types of correlation approach. And later on, I will discuss my proposed algorithm, that is CRA algorithms. And later on, I will conclude the paper. So basically, what is a big data? Big data is a term used for enormous data set, which become orders to process by our traditional approach. In this, here we have to use some distributed mechanism to process such kind of data. So big data processing becomes intensified as the data acquires velocity, and it's also known as a streaming data. So streams of data can be generated from IoT sensor network, internet network traffic data, stock market, etc. So real-time data processing, basically unbounded streams of data from various sources which continuously proliferate over time. And this sustainable proliferation of data stream needs to be processed in real-time mode and has to be synchronized with processing capabilities. it requires some distributed mechanism. Processing of data streams cannot be performed at once. It requires some finite data elements from unbounded data sets. So here it is example of a sliding windowing mechanism where our data streams is generated from one end, and it's a particular window interval is defined where a different number of data streams are assigned and various transformations and actions is applied over a particular data window, and it slide in a particular fashion. Therefore it depicts a sliding window mechanism. So there's various types of correlations, like we will say that suppose we have some X and Y streams, and when X streams is dependent on that Y streams, like at the increase of X data stream, is it known as a positive correlation, whereas uh, we can see it's a negative correlation when data streams in X direction. When the increase in data streams is X direction, it's basically we can say that this such kind of data and such kind of behavior, we can say that it's a negatively correlation. And when it will show no correlation, when there is no, we cannot identify any relationship between that X and Y, we can say that it comes under no correlation. So there is different methods to perform association between two data streams. Like most general that correlation approach is Pearson correlation. By this equation that X and Y, we can able to calculate that coefficient of correlation, and there are some limitation of this Pearson correlation. Like it is very sensitive towards outliers, and it is also so some it's not perform accurate in when data acquires some heterodasticity. So we can use a rank-based correlation in place of Kendall and that Pearson approach. So there is two types of rank-based correlation, like Kendall correlation and Spearman correlation. So, so what is rank-based correlation? First, we have to place some we have to assign some rank to a data streams in a particular order, whether it is increasing or decreasing order, and we have to here D identify some difference between the rank, and defines the number of element present in a particular window, and we have to calculate F when there are some when data streams acquire some similarities or some repeated data, then we have to calculate the F. So so we can use some rank based correlation, and also we can use some candle correlations. And candle correlations, like as as is basically a group that a total number of that items present in a particular group, and total number of items in a particular window. So basically I will explain what's the this rank based correlations define. Like this is a particular example of a rank based correlation where a particular, suppose a window consists a size of 5, and it consists 5 different items. So here we have to assign a rank, a multiple scanning has to be performed, like to assign a rank to a particular data streams, we have to pass it through multiple scanning. Like if we have n number of data items in a window, then we have to perform n minus 1 number of scanning. So but in real time processing, we have to reduce this scanning. So so these are the some existing challenges we are facing in that rank based correlation. Like we have to form a single scanning mechanism, it should be more noise tolerance, and it should be reactive processing, and it should be processed in a online manner, because in existing rank-based correlation cannot be performed in online mode. Therefore, we have came up with some CRA algorithm where we can perform it in real-time manner. So what is this CRA algorithm? To determine linear relationship in real time with two data streams. CRA, basically it performs three different operations like compare, reduce, and aggregate. So in compare, a data streams is compared, whereas in reduce phase, this compared data the data streams is assigned with 1 and -1, and in aggregation phase we have to aggregate the whole results. So basically this diagram depicts the CRA algorithms clearly. Like we have two different streams like F1 and F2 streams, and first we have to make different comparisons, and based on this comparison we have to assign that +1 and -1 based on this comparison, and also some level wise comparison is also occurred here, and this number is assigned here, and we have identified 6 different parameters like h1 l2 h1 l1 and h2 l2 and s1 and d1. So basically these comparisons and this aggregated result is stored in this 6 different parameters, and these parameters basically h1 indicates the positive similarity between first data streams, whereas l1 indicates similarity between that first data stream, as such that h2 and l2 for second data streams, and s and d shows the positive similarity between first and second data stream, that is S and D1. Okay. So based on this, by putting the values of H1, L1, H2, L2 in these equations, we will get the we will calculate that what the associativity between the two data streams. For that, we have to calculate the weight. What is the weight, whether it is negatively correlated or positively correlated. For that, we have to identify, we have categorized into 3 different cases. Like in first case, we have to check for this equation. If it is lies under these equations, we have to check whether it is negatively correlated or positively correlated. Therefore, we have formed 3 different cases. Based on these cases, we can identify, we can explain, I can explain this with the help of simple example. Like we have 2 different streams like X and Y. It consists different data streams. So suppose this is a current, the current arrived data streams is mentioned here, and at the same time the aggregated result is mentioned. So when the 1 and 6 is arrives, the data is aggregated in these variables, and when the 2 and 5 is arrived, the simultaneously data is aggregated here. So once the 6 and 1 is aggregated, we will get the values here, h1 l1, that is 5 and 1, h2 and l2, that is 1 and 5, s and d, that is 2 and 4, and we will place these values in our equations. So we will get here 0.66 values here, but we have to calculate that weight, in which case it is line in case number 2. By this equation we can form that it is minus 0.66, which is negatively correlated. With the help of this example, we can understood that. So I have compared this result with some existing correlation approach like Kendall, Pearson, and Spearman. So for sample size which is less than 100 units, we can say that it is lie that between that Pearson and that Spearman correlations, and when we will increase the sample size, it will lies, or it is closer to that all the existing approaches. And when the sample size is greater than 1,000 unit, it lied into these boundaries of some that existing approaches. So we can use this CRA approach in online manner as well. Okay, so what's the conclusion that I have derived, that proposed and implemented CRA correlation algorithms, and results are generated and compared with existing algorithms, whereas CRA algorithm shows similar patterns as compared to Pearson and rank-based correlations, and space and time complexity of CRA algorithms is generated, that is order of 1 and order of n respectively. So thank you.
Okay, thank you for the presentation. I'm asking if there are any questions for
I
the
have a
authors.
quick one.
Yes, please.
Just more a curiosity, I'd say. If you could make some examples of streaming use cases where CRA could be applied, so to detect correlation, just to make some examples.
Okay, like in any situation where we have to form some dependency between any two streams, like for example, a stock market predictions. Suppose if we know that for example, a stock of particular companies increase in a particular rate, and we have to identify whether the stock of some another company, how much that is dependent. So by this approach, we can, by correlating between one companies to some different companies, we can find out that how much that is correlated. So some in real time we can calculate it, so that it can be beneficial for the investor to invest or to make decision in real time. So in such kind of applications, we can, it is useful, it is beneficial.
Okay, thank you.
Thank you. Any other questions, curiosity, or something not clear related to the work from the audience? I don't have a questions, but again, a curiosity. Did you see any, or again, do you envision if you, the next step of this work, let's say, what you can do, what you can improve, if there are something that you are not completely satisfied or something like that? If you can elaborate a little bit on this.
In future work, actually, I have to optimize it for repeated data. Actually, when the streams consist mostly repeated data, in such situation, it will not provide in data. It should be optimized in that direction also, when data streams consist of repeated data. So I'm working in that direction also.
What do you mean for repeated data in this context?
For example, suppose data streams is static, or we can say that suppose
like a database or something like that. So you are streaming data that you know in advance.
No, not like this. Suppose, for example, repeated data in the sense the pattern is constant. If we have a simple,
okay,
which
sorry,
has a
understood.
constant value. Yeah.
Okay, understood. Thank you. So we have time for another questions, if any. Okay, so thank you again for the presentation. Now,
Thank you.
thank you. We in 5 minutes we will start the next keynote talk by Marcos Assunção. So please stay with us. So let's have a 5 minutes or more or less 5 minutes break. So at 6:15 we will start again. Okay. Thank you.
Hi, nice to see you. Can you try to share the screen?
Yeah. I can.
Okay, so that we can try.
Can you see the slides?
Yes, thanks, perfect.
Okay.
So I think we can start with the last talk, which is a keynote talk by Professor Marcos Assunção. And thanks again, Marcos, for accepting our invitation. And Marcos just moved as a professor to Montreal at ETS, which is the equal to the Technologie Supérieure in Canada. Sorry for the pronunciation in French. And he was previously a researcher at INRIA, which is the French Institute for Research in Computer Science and Automation. And before that, he was a research staff member at IBM Research. He also a PhD in computer science from the University of Melbourne, where he worked with Rajiv Kumar Bhuya on resource allocation, and is currently working on reinforcement learning for reconfiguring data stream processing application and elasticity of data stream processing application in the context of edge and fog computing. So we are working on very similar topics in this period, and the title of the talk is Towards Elastic and Sustainable Data Stream Processing on Edge Infrastructure. So as you can see, we have again edge computing as a core issue, because it's an important topic now in data stream processing. So thanks again, Marcos, and I leave the floor to you. Thanks.
Thank you, Valeria, for the invitation and for the introduction. So, as Valeria mentioned, I just moved to Canada in March. So after a couple of weeks of quarantine, I started working at ETS. So as I've just started here, I'm gonna be presenting some work that I did with PhD students that I supervised in France before moving to Canada. A little bit of work that I performed with a student that I co-supervised in Australia. So, and the topic is elastic data stream processing on edge infrastructure. So Vincenzo, during his talk, he provided some motivation for some description and a nice introduction of data stream processing applications. So I'm just going to go through this quickly. And so in multiple application scenarios nowadays, we like a monitoring of operational infrastructure, precision agriculture, detecting anomalies of existing systems or fraud. We have sensors being deployed in these sensors, they collect a lot of data, and this data is often created in the form of continuous data flows, continuous data streams that need to be processed quickly. The target infrastructure for processing this type of data is often the cloud. When we process this data in the cloud, we often we divide the system into multiple tiers of data collection and processing, so that the system can grow, each tier can grow independent from one another, and it can scale up. The problem with that is that what I call here data motion systems, like message brokers, they increase the end-to-end latency of data processing. So that's often an issue. Edge computing appears as an interesting infrastructure because some of the processing can be done on edge computing resources, which are closer to where the data is actually generated. And in this way, we could potentially reduce the end-to-end latency. So just to make it clear here, what I call the edge is anything that is virtually outside the cloud. So I'm not talking about the devices, the sensors and the controllers themselves, not talking about the deploying data stream processing on this type of devices, but devices that interface with the sensors and these actuators. So the devices that can run some an operating system and that can run some data stream processing applications. So anything that is virtually outside the cloud here, I refer to as edge computing. So both Vincenzo and Gabriele, during their talk, they described elasticity. I'm just, again, going to go through it here quickly. So when we talk about elasticity from a resource management perspective, we can see that in the cloud, the way it is done, often the cloud provider deploy resources and a hypervisor on top of which a user or a service provider can create instances of VMs. And these instances can be created to match a given workload. And in addition to that, if we use some container-based virtualization, we also have containers running on top of our virtual machines or on top of the resources themselves. So we have multiple issues of resource management in this infrastructure, multiple levels in which we have to address the management of our resources, and we have to plan for capacity, plan for the placement of the applications on top of the available resources. So one of the key issues is often when and how to scale out or scale in the underlying infrastructure. So data stream processing applications, as mentioned earlier, they are structured generally as directed graphs. And these graphs, the vertices of these graphs are operators that perform some processing tasks over the incoming data or the data sources that interface with the actual data sources, that the devices that collected the data or that generate the data. The operators, they have some properties like the selectivity, whether they drop tuples or data events that they receive, if they transform the data by applying some processing that reduces the amount of data that it receives, or whether it increases the amount of data that it receives. And they also may maintain a state, or they can be stateless. There are several issues when deploying this type of application onto available resources, but one of the main issues is how to place the operators on top of the existing the available resources. Things are more complicated than what is showed on this picture, because we can have the logical graph, which gets transformed into the physical graph that gets deployed on top of the existing resources. But that's the main idea. So when we split the graphs, and this application should be deployed across cloud computing and edge computing resources, things that we need to consider to make the applications elastic. We need to be careful with the initial placement where we place these resources, because if we move where we place the operators, because if we need to move these operators, that might incur an overhead for adapting the application. So I'm gonna come back to this factor later when I present some results. The application reconfiguration, we need to be able to adapt the application if the underlying infrastructure changes or if the load changes. And we need to cope with the operator state and fault tolerance mechanisms. So when considering the edge computing resources, we have to be aware that the edge computing resources, they might be more limited than their cloud counterparts. Some of these resources, they might be powered by batteries or renewable energy sources like solar panels. And when processing on top of these resources, we need to consider these factors as well. So, and one of the issues, like Vincenzo mentioned, is what should be offloaded or what can be executed, what kind of a processing test can be done on the edge computing infrastructure. So in our work, we try to model this problem. We model the infrastructure as a graph that comprises computing resources and logical links. These resources, they have CPU and memory capacities, and the network links, they have bandwidth and latency. The application graph contains operators and streams. The operators, they have some CPU capacity required to process an event. They have the memory demands for loading the operator, the selectivity, and the data transformation factors that I described earlier. When considering how these applications get deployed on the resources, the operators, they have a message queue. There is a dispatching service that is responsible for routing the incoming data events or tuples to the operators running on a particular resource. And then the data transfer service that sends the data, that has a message queue and sends this data to other resources or other operators running on other resources. The events are handled in a first come, first served basis. And one of the main metrics that we try to optimize is the end-to-end latency of the paths. So the end latency of a given path here is the sum of the computation time and the communication time of across a given path from one source to a sink. And the placement goal is to minimize the aggregate end-to-end latency of all paths. We use this metric instead of focusing only on the critical path or minimizing the make span, because we consider that applications where the processing, the data source, the processing, and the sink might happen only on the edge without going into the cloud. So that may create a data path by itself. So we need to optimize all the paths in order to optimize the application. So we've experimented with some power meters to be able to compute the amount of power consumed by Raspberry Pis when running some data stream processing applications. So we run some experiments with Apache Agent, and we build a power meter using some analog to digital converters, and we played with that and tried to compute it, to create some power consumption models. That was done with the PhD student that I co-supervised in Australia, and so the more details are available on the paper on how this infrastructure was used, and the details on the how to build the power meter are available on GitHub. Then one of the main works that we performed in Lyon was the reconfiguration of using reinforcement learning for reconfiguration of data stream processing applications. So why would someone want to reconfigure an existing data stream processing application? Well, these applications, they are supposed to be long running, so they are going to run for long periods of time. The workload conditions may change during this the execution of this application. So this way, the initial placement might not be ideal. We may need to adjust. And one factor that is not considered in detail in our work, but we would like to consider, is that the edge computing resources, they might be more prone to failure than the resources on the cloud. So we need to adapt the application to cope with this type of problems. So the goal was, we had two goals in this work. One was to find a new placement that improves the aggregate end-to-end latency. And a second work that I'm going to talk more now is minimizing the aggregate cost, which considers not only the end-to-end latency, but other factors that we might have to consider as well when executing on edge computing. So to compose the aggregate cost, we use the aggregate end-to-end latency itself. We also take into account the traffic that crosses the internet, because we have to, that incurs a cost in terms of overhead, but also we need to pay for the usage of, if we use a cloud provider, we need to pay for the usage of such links and for transferring such data. So we have to consider the monetary cost of communication, the data that goes from the edge to the cloud and vice versa, and the reconfiguration overhead. Here we use a pause and resume approach, in which we pause a given operator that is going to be migrated. We pause the upstream. We accumulate the data, then we compute the time that is required for migrating a set of operators. We take the longest time of these operators that are migrated, and that's the overhead. And then we take into account the time for migrating the operator, the code, and the state itself. So then all these metrics, we use a simple additive weighting scheme to compute the aggregate cost, where we assign weights, different weights to each metric that compose the aggregate cost. We model the decision process of deciding how to change the placement, an existing placement, as a Markov decision process. So in an MDP, we have a set of states, and each state we have a set of actions that can be taken. And when we take an action, we move to another state. We have the agent that is performing such MDP receives a reward. So in our case, each state contains a valid placement. An action consists of either migrating an operator to another resource or maintaining its current mapping, its current placement. And the reward tries to reflect the improvement in the aggregate cost that we have under a new state. So then with that, with this MDP, we generate a lot of episodes. To generate the episodes, first we traverse the application graph using a breadth first search algorithm. With that, we compute a list of operators, and then we consider one operator 1, if we move it to an X resource or Y resource, what that generates the beginning of a new episode. And we go until the last operator, here is termed as the terminal node, to finish an episode. When we consider all the operators, that's how they could be migrated, and that is the end of a given episode. So an optimal policy here would be something that specifies the best actions that can be taken into the states in a way that the reward is maximized. As we may end up generating a lot of episodes with possible placements, we organize these episodes using a Monte Carlo tree search. So under here just adapting an example from Sutton and Bartu's book, in the Monte Carlo tree search, we have several 4 steps. We have the selection, expansion, simulation, and backup. So in addition, so the episodes, the root of this tree is the current placement that an application is under. So we start from that placement. We consider them for each operator. We create a node. We expand a node. Each node of this tree contains, in addition to a valid placement, the number of times that the node was visited, an action value, which is known as the Q value of a given action, QSA. So the actual, I will use a term here, it's not exactly that, but the utility of taking a given action under a given state. So taking actual A under state X. And the number of times that a given action was picked. So the simulated episode is created using a tree policy, which is a policy used to navigate the tree, and a policy using, also we get to a node that has not been explored, and we expand that, how we go until a terminal node. So a rollout policy here is just random. We take random actions until we reach a terminal node. Often in this type of problems, we have a dilemma between exploiting nodes that we know already, or taking actions that we don't know, for which we don't know the value yet. And if we only take the actions that are known, then we may end up on a local maxima or local minima. So we need to balance between exploration and exploitation, and I'll come to that next. So one way to update and to compute these values for the actions that we take is using Q-learning. So if we use Q-learning, we always pick the value of being in a given state is the value of the best action that can be taken on that state. And to compute the Q values of the actions under a given state, we use this formula. Here which essentially has a learning rate and a discount factor that considers how the past states are the weight of the past Q values on computing the action value. So if we use a fully greedy policy, we select how is the best policy under a given state, the best action under a given state. But that limits the improvement that we can have in the reward. We may not get to the optimal. So one solution that is often adopted is using a greedy policy, epsilon greedy policy, in which we do exploitation with a probability, with a high probability, but we also explore unknown actions with a very small probability, but from time to time, the algorithm or the agent will pick an action that has not been explored, and we will expand the nodes in that tree and then discover new actions and their values. Other algorithms that we considered as well for the tree policy for picking the nodes and that to generate the episodes are and computing the Q values are UCT. UCT tries to assign a bonus to uncertainty of a given state action. So it uses the UCT formula to compute it, which presents a scalar number here, a scalar variable that specifies the exploration constant. So it just tries to assign a bonus to actions that have not been picked yet, and with that we can do exploration. And SARSA is similar to Q-learning, but it goes one step forward, hence the name SARSA, state action reward, state action. So it goes one step further when computing and updating the Q values of those actions. So we built a discrete event simulator to simulate the data stream processing applications, and then evaluate this reinforcement learning algorithms for pre-configuration of these applications. So it's the source code is available. It's a simulator built on top of Omnet++, which is a network simulator. We modeled a scenario where we have two cloud servers and two sites of with 20 resources each. The resources are modeled as Raspberry Pis, Model 2. They are interconnected by a wide area network, which is our internet in this case. And the network latency for the experiments that we performed is modeled based on existing work that evaluated the delay between sites of Amazon Cloud, for instance. So we created some graphs to emulate the applications, simulate the applications that we consider. These graphs are based on the size of the applications in the RIOT benchmark. So we come up with 11 application graphs with either simple or multiple application paths. We vary the properties of the operators according to this table presented here. 20% of the operators, they keep state, they have state, so we have to consider them and their overhead when we change a given placement. And so the initial placement of sources and sinks are the critical path is always placed on the cloud. So we consider that the sink in the critical path of an application is always placed on the cloud. And the budget that we give to the reinforcement learning algorithms to do that step of expanding the tree and rollout is 10,000 iterations. So the initial placement scenarios that we consider, from which we adapt, we try to come up with a better placement, is cloud only, where all the operators are placed on the cloud. And TSAP, which is the tenacious cloud edge placement, that is an algorithm proposed in the state of the art, which essentially creates a list. It sorts the operators, the resources, picks the operator, tries to put the resource into the middle of that list. If it doesn't fit, then resource on the edge puts the resource on the cloud. So the reported values here, they are averages of multiple executions and normalized by the maximum observed in each of these solutions. So I'm not gonna go into too much in detail here, but the main message here is that when we start from placement and original placement based on cloud only, and we then execute the algorithms either with SARSA or UCT, we can reduce the entrant latency if we assign a weight of 1 to consider only the aggregate end-to-end latency. So if the algorithm, the solution is oblivious to other metrics and considers only the end-to-end latency, starting from cloud only, we can still reduce the other metrics by chance here, but it's not, the algorithm is not actually trying to optimize that. But if we start from an algorithm that does already some optimization by putting some of the operators on the edge, then it's a different story. We can still minimize some latency, but we can minimize some traffic, still by accident. But as we don't pay attention to the monetary cost of such decisions, we can be more expensive than the other algorithms. If we assign equal weight to monetary costs, one traffic, and aggregate end-to-end latency, then we can see that if we start from cloud only, we can minimize all these metrics. Even if we consider the TSAP, we minimize the monetary cost here and the event traffic. The issue then is if we consider this 3 components of the aggregate cost, like the monetary cost, event traffic, and aggregate end-to-end latency, but we ignore the reconfiguration overhead, we can see that the algorithms, they can have a considerable cost of migrating operators when we start from an algorithm that already does some optimization by placing some of the operators on the edge computing resources. So if we need to change those operators, then it can get a bit expensive. So the lesson here is that if we try to adapt an existing placement where where the placement already performs part of the tests on the edge, then we have to take into account the reconfiguration overhead very carefully. So if we consider equal weight to all the components of the aggregate cost, then we can see that if we start either from cloud only or from TSAP, we can minimize all the metrics, including the reconfiguration overhead. And so just to summarize what I've presented here, we've modeled the data stream processing application, and then we used the Markov decision process to model the actual decision of how to change an existing placement, an initial placement, and adapt it. We evaluated 2 classic reinforcement learning algorithms. We proposed a means for considering multiple metrics, but it would be interesting to use other things like Pareto, analyze Pareto fronts, and consider more sophisticated methods of considering multi-objective optimization rather than the simple additive weighting scheme. So we would like to focus more on that. And also, we've used some classic reinforcement learning. We are looking into how we could use more modern reinforcement learning techniques for the reconfiguration problem. And that's pretty much what I had to present. And thank you again for your time, and I'm available to answer any questions you might have.
So thanks, Marcus, for the very interesting talk. And is there any question from the audience?
I have one.
Please,
Sure.
Gabriele.
So first of all, thanks for your talk. I would like to ask if you could add some comments on how you define the state space in your MDP model, because if I understand correctly, the state considers the current placement of the application, but I'm wondering if you also include some information, for example, on the presence of stateful operators or the current workload, other details.
So in the state, we consider the placement, the assignment of the operators to available resources. In the state itself, we don't consider information about, we have information about the resources that are available, but we don't have information about the state of the application itself, the state of the application is under. So when we compute the episodes, we check whether a given operator could be hosted on a given resource. That's when we actually check whether a placement is valid or not, whether a given resource could host an operator. But in the definition of the state in the MDP itself, we don't consider that.
Okay, thanks.
So I have a question. Have you experienced convergent problems in the experiments using reinforcement learning?
So the way here we, so this even though they are classic reinforcement learning algorithms, they have like UCT, SARS. They have multiple parameters that have to be taken into account when configuring them. So we ran a bunch here. I'm presenting only the results with the best, with the best set of parameters. So we run experiments with multiple parameters. We did like a parameter sweep for running that, and then we identified the parameters that worked best, and the results that we present were performing the simulations with those parameters. What we noticed is that, and it's something that we would like to address in future work, and it's often mentioned in the literature, is that some of the algorithms, they are not that stable to provide for some solutions, is SARSA, for instance. So they might perform well for an application that has a given structure. It might not perform well under others. So there are some issues in the stability, I would say, of some of these algorithms, and it's something that we would like to address in future work. But sure, it is an issue.
Okay, thanks.
Nice.
Is there any other question from the audience? I'll check on Slack, not on Slack. So it seems to me there are no more questions. So thanks again, Marcus, for the nice presentation. And
thank you very much for the invitation.
Thanks. And this is the last talk of our workshop. So I think we can conclude here. And thanks to all of you for attending the workshop, and we hope to meet in person next time, hopefully for the next edition of the workshop. So I don't know if Massimo or Gabriele would like to add something.
Not really. I also want to thank everybody, obviously, and hope to see you soon.
Yeah, I also would like to thank the attendees for attending the workshop today, even if it is in a line manner, but I hope that we did a good work for organizing the workshop in this way. Hope that in the next year, the situation will be much better and we can come back to do workshop in a traditional manner.
Yeah.
So thank you so much.
So thanks.
Thank you, everybody.
Thank you.
And
Thank you.
bye.
Bye bye.
Bye-bye.